just actually really just starting to get into them.
Okay.
So we are just kind of learning like what an arithmetic sequence is.
Okay.
And I was just kind of confused on like what it is specifically.
Okay. First of all, have you just done arithmetic, or have you also done geometric?
I think just arithmetic.
Okay. Arithmetic sequences are defined what they essentially are is any sequence that's separated by a constant amount between each term.
Okay.
That's an arithmetic sequence because of that. Separated by 3. And that makes D 3. So if I wanted, say, the 5th term of this sequence, well then a sub 5 would equal to the first term, which is 1. Isn't always 1, but in this case it's 1. Plus the common difference, which is 3. Since I've got an n of 5, this is 5 minus 1. So that gives me 1 plus 12. 13 should be my 5th term, and it is.
Yeah, okay.
The advantage of this nth term formula is that if I wanted the 132nd term, I could get it. Whereas I certainly wouldn't want to have to write out 132 numbers in that sequence.
Yeah. Okay.
Okay, and then the other key thing about sequences is what is the sum of the sequence. In other words, if I want to know the sum of the first 5 terms, that's the first term plus the last term divided by 2 all times the number of terms. I think that's what it is.
Okay.
Now, I can test it by plugging it into this, and I can add these up. What's that? 12, 22, 35? So let's see if I've got my thing correct. Is S sub 5 going to be 35? Well, n is 5. First term is 1. The 5th term is 13 all over 2. 5 times 7 equals 35.
Okay.
So these two formulas are what you want to memorize with arithmetic sequences. And that'll get you a long way. In other words, that'll answer most every question they're going to ask you about sequences. But you always want to start out with these general formulas. Now, a lot of times you don't necessarily know the last term. But it kind of depends on the type problem. Do you have any specific problems at all?
Yeah.
Okay, good.
So
look at them.
The first one is to find the first 4 terms of each sequence.
Okay.
And the first problem is a sub n equals -2 to the nth power plus 7.
Okay. What's the first term? And this is where n's going from 1 to 4. It says find the first 4 terms of the sequence?
Yeah, find the first 4 terms of the sequence.
Let's write the first term.
Okay. You just plug in 1 for n, right?
Uh-huh.
So it'll be -2 to the first power plus 7. It just comes out to be 5.
Okay. What's the second term? Now this is in parentheses, yes? Or no? Then minus
what?
Is it?
Yeah, it's -2.
Okay, but it's
not
-2 in
it's not.
No?
No, it's not in parentheses.
Okay,
No.
because that's going to matter when we do an n of 2.
Okay.
Okay, so what's the next term going to be?
3.
Right. And then an n of 3.
It'll be -1.
And an n of 4.
It will be -9.
Yeah, now notice that this is not an arithmetic sequence. It's also not a geometric sequence.
Okay.
Usually when they teach you sequences, those are the first two they start with, are arithmetic and geometric.
Mm-hmm.
The arithmetic is every term is separated by a constant amount, which is not true here. Geometric, every term is a constant ratio of the previous term. In other words, if I had the following sequence, that's a geometric sequence because every term is double the previous term.
Okay, so I guess we learned both geometric and arithmetic.
Well, you're learning more than that because the one you just gave me is neither. And there's a lot of sequences. This is the one you just gave me is an example of one that is neither arithmetic nor geometric, which is fine. You know, there's nothing wrong with that. It's just, and I'm not quite sure how far they're going to take this with you. Writing out the first 4 terms is not that hard. Okay. What else do you have?
The next one is a sub n, and this one is in parentheses. -1 in parentheses to the n plus 1 power plus n.
It's going to be an alternating sequence. By that I mean one term is going to be plus, the next term is going to be minus, the next term is going to be plus. And alternating sequences have this characteristic where it's a -1 either to the n or to the n plus 1, depending on whether you want the first term to be the negative or positive.
Okay.
So what's the first term here? In other words, what's a sub 1?
It's going to be 2.
Yeah. So we'll write that. What's a sub 2?
Is going to be 1.
A sub 3.
Is going to be 4.
And a sub 4.
Is going to be 3.
Yeah, and I said it was going to be alternating. I lied. This makes it not alternating. Usually when you see a -1 to the nth power or a -1 to the n plus 1, what that's going to do is change the sign. You'll notice that this part of it went plus minus plus minus plus minus. But it turned out that this part of it was growing faster than the minus part. So we never did have a negative term in the sequence. But when you study sequences in calculus, this is a key term for alternating sequences. In other words, every term is going to switch back and forth between plus and minus. Even though this one does not do that, it kind of does. This part of it does that. The -1 to the n plus 1. In other words, if I do this, it's 1, -1, 1, -1, 1, and so forth.
Oh, okay.
And the only difference between this and if I had the following sequence where I put the -1 and I started it to the nth, Well, that sequence is minus 1, 1, minus 1, 1. In other words, it's still alternating. It just starts with the minus instead of the plus.
Yeah.
So sometimes you'll see it to an n plus 1, sometimes you'll see it to an n, depending on whether you want the sequence to start with a negative or a positive.
Okay.
Okay?
The next one wants us to find a specific term of each sequence.
Okay?
So it wants us to find the fourth term of this sequence. A sub 1 equals 5. And then a sub n equals negative 3 a sub n minus 1. Plus 10. And then n can either be greater or equal to 2.
Okay. And they want you to find the a sub 4?
Yeah. They want us to find the fourth term in the sequence, yeah.
Any way you can, or?
Yeah, it doesn't say a specified way.
This is not the explicit nth term. This is the recursive nth term formula.
Okay.
And the difference is that the recursive formula
Oh, I remember learning about this.
always a function of the previous term. In other words, to know the fourth term, you need to know the third term. To know the third term, you need to know the second term, and so forth and so on. If they would have given us the third term, then the fourth term would have been a piece of cake. So, let's see. What's a sub 2? We'll just do it the hard way. There may be an easy way to do this, but I'm not sure what it is.
Do you just have to plug in 2 for n?
Yes.
Okay.
Now, notice that when n equals 2, this term becomes a sub 1.
When n equals 2. Oh.
And that's
okay.
5. So, we know that a sub 2 is minus 5. Now we can figure out a sub 3, because each nth term is a function of the previous term. That's what this definition, how it works. I've never quite understood why we have a recursive formula, because you don't often know the previous term. But when you get into infinite series and calculus, you'll see more reasons why this is a useful formula.
Okay.
But let's finish it. What's a sub 3?
Is going to be...
Let's just fill it in. In other words, spot by spot. So it's minus 3 times...
Then... well, I'm confused on how you plug in the 3 for the n minus 1 with the lower subscript.
Here's the n. So we're going to plug it in for there. So what we're really talking about is a sub 2. In other words, that's going to be a sub 2, which we just calculated to be minus 5.
Oh, so you plug in minus 5,
right?
Minus 1.
Plus 10. You don't plug in minus 5 minus 1. In other words, this means if I'm trying to find the third term, that means what the second term was.
Okay.
In other words, the nth term is a function of the previous term.
Okay.
So we're going to figure out a sub 2 based on our knowledge of what a sub 1 is. Then we're going to figure out a sub 3 based on our knowledge of what a sub 2 is, which
Oh, okay.
25. And now a sub 4 is going to be minus 3 times
That's
a sub
20,
3,
and that'd be 25.
correct? So that would be minus 75 minus 65.
And that's the fourth term.
That's the
Okay.
fourth term. Yeah. Now, turns out this is an alternating series, which is interesting.
Uh,
I would have never put this as an alternating series. But by that, I mean it goes from plus to minus to plus to minus. And it'll keep doing that. Because since every term is a function of the previous term and we're multiplying that by a negative number, then it's just going to keep bouncing back and forth between plus and minus. Okay, what else?
Okay, the next one is, it wants to again find the fourth term,
Okay,
and a sub 1 equals 0, and then a sub n equals 3 to the ace power n minus 1. Not ace, the a power n minus 1.
all in the exponent?
It does the thing where, so the a is in the exponent, but then the n minus 1 is in a drop down.
A subscript?
Yeah, subscript, sorry.
That's the way I've written it.
Okay, yeah.
And that makes sense. In other words, we're still defining a sub n as a function of the previous term. The previous term is a sub n minus 1. So you write it with both subscripts down like that.
Okay.
Okay?
And then n can either be greater or equal to 2.
Yeah, notice why that is true. In other words, why they put that in there is because if n is 1, what's a sub 0? We don't have an a sub 0. So you can't refer to the previous term if n is 1. Okay? So a sub 1, they're telling us is 0. So let's just do the same process. What's a sub 2?
A sub 2, if a sub 1 is 0, a sub 2 would be, well, wouldn't you put 3 to the 0 power?
Yep.
So that just becomes 1, right?
That's correct.
Yeah.
Okay, so a sub 3.
A sub 3 equals 3. Isn't it because you just put 3 to the first power?
Yeah, hold on a second. I'm confused myself. Let's see. A sub 3 is 3 to the a sub 2. A sub 2 is 1. Yep. Okay. And what about a sub 4?
A sub 4 just becomes 9 then, right?
Correct. No? Hold on.
Oh, third power. It becomes 3, 9 times 3, 27? 27 power? Or 27?
Yep.
Cool.
This is a little off the subject, but it's still worth noting, I think. It's a very interesting mathematical fact. Have I ever given you this problem? Have I ever talked to you about this?
Oh, a little bit, but it was briefly when we were like doing SAT prep and such.
That's equal to 16. Guess what this is equal to?
Isn't it like something much, much higher?
7 trillion.
Yeah.
Just by the fact that we're using 3 instead of 2.
Why is that?
Well, because you work from the top down. In other words, there's no parentheses. So first I do 2 squared, which is 4, and then I take 2 to the 4th power, which is 16. Well, when I drop down and I take 3 cubed, that's 27th. And then 3 to the 27th power is 7 trillion.
Oh, really? Oh, okay.
Okay? And
So four would be really high too, right?
yeah, but when you study there's a branch of mathematics that deals with extraordinarily large numbers. And I'm not talking about numbers that can be represented by scientific notation like 10 to the 64th power. That's a
Yeah.
large number, but it's nothing like the kind of numbers that they deal with when they use this kind of notation. And when I first studied a little bit, I couldn't figure out why they used 3. 3 is their base for talking about large numbers. You can imagine if I added a 4th exponent, how big that thing would be.
Yeah, it's kind of funny. I'm like typing this into my calculator and it just says
Yeah,
overflow.
yeah, 3 to the 7 trillionth power is enormous. I mean, we're talking
Uh,
way more than the number of molecules in the universe. But there are applications. In fact, there was a contest once where the goal of the contest was to come up with the largest possible number. And it couldn't be infinity. It couldn't be somebody else's answer plus 1. It had to have some sort of meaning. In other words, like the number of molecules in the universe. Only
uh,
when they deal with these kind of numbers, the meaning is, I can't even think of an example of what it might mean. But
like almost like number of galaxies, but that's infinite too.
the number of what?
Of like galaxies in the universe.
Oh, galaxies?
Uh,
That's questionable whether that's infinite or finite. That's still
yeah.
up in the air. This is
Mm,
how you would write 3 to the 3 to the 3 using those upward arrows. And so you can actually do multiple arrows, and I'm trying to remember what that means. But you can imagine that you can talk big numbers in a hurry using this kind of notation. Um,
yeah.
yeah, no, the number of galaxies in the universe is actually fairly finite. Well, they don't really know. Half the physics community believes that it's infinite. The other half believe it's finite.
Isn't that because they don't know if the universe has like stopped expanding yet or not?
Well, yeah, there's all kinds of things they don't know about the universe. They don't know that it's just one universe. They think that there might be an infinite number of universes or
Yeah.
parallel universes or what they're now calling the multiverse. Uh,
Mm,
but I'm inclined to truly believe in, I don't really believe in infinite. It's a mathematical concept, but you can't tell me one single thing that's ever been proven to be infinite. Uh, Nothing in
is there? There's nothing that's ever
no,
been proven to be infinite?
nothing in the physical world that I know of has ever been proven to be infinite.
Oh, wow.
The number of molecules in the universe is like 10 to the 50th. That's not even that
Yeah.
many. So that's not anywhere close to infinite. No, what would be infinite? And whether there's an infinite number of universes or not, they're never ever going to be able to prove that one way or the other, I don't believe. So
Uh,
anyway, not to get too away from your stuff matter here. Let's get back
yeah.
to your stuff.
Okay. The next one is determine whether a sequence is convergent or divergent.
Okay.
And can we just go over what those are
Uh-huh.
kind of a little bit?
Yep. Here, let me give you a couple. The two most famous ones are this one. When they talk about a sequence being convergent, they really mean a series. In other words, a
Mm,
series of all of the terms. Okay? That
okay.
series right there, which I could write as 1/2 to the n. Have you learned sigma notation yet?
Yeah, we have a couple problems kind of towards the end of this that are segmentation.
That series that I just wrote could be written like that.
Okay.
That is convergent. Okay? Meaning that even though n goes to infinity, this thing converges to a number. And the way you can describe why that is true is if I draw a square, we know the area of this square is 1. Well,
Yeah.
there's 1/2 the square. There's 1/4. There's 1/8. You can see where I'm going with this.
Uh-huh.
There's 1/16. Even if I go all the way out to infinity, I'm just going to come up with 1 square. In other words, if I add every single term, I'm going to get 1. So
Yeah.
that sequence adds the 1. It's convergent.
So it converges to like one number.
Convergent means that it converges to a number. Sequences that would not converge would be if that number is 1.1 or anything greater than 1. In fact, it only has to be 1 for it not to be convergent. Notice that this sequence here, the one I've got circled, is just 1 plus 1. I should call it a series. It's a series. Plus 1. In other words, it just keeps going. So that's going to add to infinity if n goes to infinity.
Yeah.
So this is divergent. Okay. And determining whether a series is convergent or divergent is a semester's worth of study in math. Believe it or not.
Oh, wow.
And I say that because it's taught in Calc C. That's where you get to it.
Okay.
And there are at least 10 tests that I know of for determining whether a sequence is convergent or divergent. 10 different tests. Each one of them more complicated than the other. Some of them are relatively easy. If you have a P series, that is convergent. A P series being 1 over... That series right there is not convergent. This is fascinating here, actually. Here, let me point this out because this will blow your mind. At least it blew my mind. If I take this series, this is divergent.
That's divergent?
Now, this one's convergent, this one's divergent.
Why is that?
Well, the best way to explain it is that those two terms always are greater than the previous term. Right? If I add 1/3 and 1/4, I get 7/12. These two terms are always previous than the previous term. So
always less than or greater than?
Greater than. In other words, what I have is a series that keeps getting bigger. In other words, if I want to look at this series as this term plus the next 2 terms plus the next 3 terms or 4 terms or whatever it takes to be bigger, then it just keeps growing. Whereas notice that's not true in the series up here. If I took the sum of those 2 terms, they're not greater than 1/2. And in fact, I could take the sum of all of the rest of the terms out to infinity and they're not greater than 1/2. So that's why this one's convergent, or one explanation, and why this one's divergent. The key is the following. If I have sigma notation, and it's called a P series, and what it is 1 over n to the P, And if P is less than 1, it's divergent. Excuse me, it's convergent. And if P is greater than or equal to 1, it's divergent. I think I got that right. I might have it backwards. I do have it backwards. It's divergent and convergent. But the P-series test, just one of the 10. There's the ratio test and the nth term test, and there's all kinds of tests to determine whether series are convergent or divergent. I suspect the ones they're going to give you are not going to be that hard to figure out. What did they give you as specific problems?
The first one is a sub 1 equals 4. And then 1.5 a to the n minus 1.
Whoa. What?
Or sorry, 1.5 a sub n minus 1.
Is what a sub n is equal to?
Yeah.
Okay. And they want the fourth term?
No, they just want to determine whether the sequence is convergent or divergent.
Oh, okay. Well, let's write out a couple of terms. We know the first term is 4. What's the second term?
The second term would be 1.5 of 4.
It's
so
times 4, right?
Yeah.
Okay, so the second term is 6.
6, yeah.
What's the third term?
Well, 1.5 times 6, that'd be 9.
Is this series growing always?
Yes.
13.5. If there's one thing, there's one test that's the easiest test to apply to consider divergence or convergence. That is called the nth term test. If the nth term test is not 0, it's divergent, no matter what. If the nth term as n, let me restate that. If the limit of the nth term as n approaches infinity has to equal 0 for it to even be considered convergent. That does not prove convergence, but if it's not equal to 0, it does prove divergence. And let's talk about that, back those other two sequences we had, because they're a perfect illustration of the nth term as n goes to infinity here is clearly 0, right?
Yeah.
Getting smaller and smaller and smaller, it's going to approach in 0 as n goes to infinity. Well, same thing here. My denominator keeps getting bigger. I'm approaching 0. So the nth term is 0 on both of these series or sequences, but one of them's convergent and one of them's divergent. So just proving that the nth term is not equal to 0 is a test for divergence only. It does not prove convergence. Both of these nth terms go to 0, but they're not both convergent. So, but in your series, the one you just gave me, we can tell that the nth term is going not to 0. And if the nth term doesn't go to 0, it's automatically divergent by the nth term test. I'm not sure how many of these tests they've taught you, if any of them. They may not have spelled them out. They may just be wanting you to look at these problems logically and see that there's no way that thing converges. The only thing that really, they're still calling these sequences?
Yeah.
So when they say a sequence converges or diverges, they mean to a certain number, I guess. I'm not sure exactly what they mean.
Yeah, that's what they mean. It diverges to a certain number. Because we went over that.
Okay, here's an example
One
of a sequence that diverges or converges to a number.
converges. Sorry.
Converges to a number. And it's a little different than series. Series is either the series sums up to a number or it doesn't. If it sums up to a number, it's convergent. If it doesn't, it's divergent. A sequence is a little different. If I take the limit of this sequence, it approaches a certain number. In other words, if I figured out what 1 plus 1/2 to the 2 power is, and then I figure out what 1 plus 1/3 to the 3 power is, and so forth and so on, and then eventually I'm going to be figuring out what is 1 plus 1/100 to the 100th power. What do you suppose this sequence converges to? And this is a sequence. This is not a series. I'm not adding up every term. In other words, I'm approaching a certain number as x gets large.
Does it just approach 1?
E.
E.
That's the definition of E. That's what E is. What you'll find if you were to do this is that you start approaching the number 2.71. And as x gets bigger and bigger, you merely add more decimals that never repeat. It's like pi.
Okay.
And the way you gain accuracy with E, if you want to be as accurate as you possibly can with E, let x be as big as possible. In other words, if I did this, if you did that in your calculator, 1 plus 100th, in other words, 1.01 to the 100th power, go ahead and do it real quick.
Do what? 1 plus 1 to the,
1.01 raised to the 100th power.
It comes to as 2.70 for E.
Close. 2.70. Now do 1.001 raised to the 1,000th power.
That comes to 2.7169233932.
There you go. Now you're gaining accuracy. And if you want to accurately estimate E, just make x get larger and larger. But this is the definition of E. And you can see that it does approach a certain number. It's approaching E, 2.71.
Oh, I see.
Okay? So it doesn't keep getting bigger. And in fact, if I called this a series, it would diverge. This would be a divergent series, because as all I'm doing is adding numbers that are getting closer and closer to this. So eventually I've got 2.71 plus 2.71 plus 2.71. The nth term is never going to be 0. And if the nth term isn't 0, then you have a divergent series, as opposed to a convergent sequence. So there is a difference. Technically, a sequence is just a list of numbers separated by commas. That's what a sequence is. That's a sequence we're looking at there. A series is the sum of a list of numbers. The series is the sum of a sequence of numbers.
Okay.
Okay. All right. What else did they ask for?
The next one is a sub n equals n squared plus 4 divided by 3 plus n.
Okay. Okay, now this is not a recursive formula for a sub n. This is an explicit formula. If I want to know the 13th term, I just plug in 13 for n, calculate what it is. If I want to know the first term, it's going to be 5/4.
Okay.
Okay. What did they want on this one? The fourth term?
Whether it's convergent or divergent.
Ah, whether it's a convergent or divergent. Well, let's list a few terms. First term would be 5/4. We can kind of get an idea. I don't know if we can or not. I'm not sure I know the rules for convergent sequences. Let's see, when n is 2, we have 8/5. So we appear to be growing. Notice the top's always going to grow faster than the bottom.
Oh, so it's going to be divergent.
It's going to be divergent because the top, the bottom, this is always going to grow. Right? Every term is bigger than the previous one. When n is 4, now we got 20 in the numerator and 7 in the denominator. Notice the denominators are growing by 1. The numerator is growing by 3, 5, 7. So if the numerators are growing that much faster than the denominators, then this sequence is not going to converge to a given number, like E. That's
okay.
Does. In fact, I'm surprised they don't ask you that. In other words, give you 1 plus 1 over n to the nth power. That's the perfect one to give you because most people are familiar with E, but most people are not familiar with how E is defined. And it's defined as the limit of a sequence, essentially.
Okay.
What else?
The next one is a sub n equals 5n plus 6 divided by n.
Okay, so the first term is 11. Second term is 8.
16.
Divided by 2, right?
So 5n equals 10 plus 6 divided by... Oh, I see. Okay.
Third term is 7. At least we're going down, so it's got a good possibility of being convergent. Fourth term is 26 over 4, 6. We seem to be converging on a number. I would take a wild guess here and say that we're going to converge on, what number do you think we converge to?
Probably 1.
I'm thinking 5.
Or 5.
And notice why. Remember when we're looking at horizontal asymptotes and end behavior and all that good stuff?
Yeah.
The ratio of the coefficients. In other words, if I look at the 100th term here, it's 500 plus 6 divided by 100. We're getting closer and closer to 5 plus 6 100ths. But this part's going to approach 0. So we are converging on the number 5. And
I see.
Of that. And it doesn't really matter what that number is. I could make that 5n plus a billion all over n. And guess where that converges? To 5. As n goes to infinity.
Okay.
Because as n goes to infinity, that part eventually goes to 0. Right?
Yeah.
And this part here goes to 5. So whatever number is immaterial, just like if they gave you this problem. If they gave you this, that also converges to 5. In other words, that is immaterial, That's immaterial. The only thing that matters is the highest degree in the numerator is 2, the highest degree in the denominator is 2, the ratio of those coefficients is 5. That would
Okay.
have a horizontal asymptote at 5, and it would approach it as n went to infinity.
Okay. Huh. All right. Well, the next thing is the last thing actually
Okay.
is find the indicated sum for each sequence,
Okay, cool.
and it starts getting into like partial sums.
Uh-huh.
So it wants us to find the fifth partial sum
Okay.
of a sequence that is a sub n equals n parentheses n minus 4 parentheses n minus 3.
Well, you can clearly do it the hard way.
And I have the formula for, yeah, that's the formula for partial sums.
What is it?
It is S of n.
N equal.
S of n equals n divided by 2 times a sub 1 plus a sub 2.
That's interesting. Plus a sub 2 or a sub n?
A sub 2.
Serious?
Yeah. Mm-hmm.
Well, okay, that's interesting because the formula for the sum of an arithmetic series is, guess what? Very close to that. But that's the last term. And this is only for an arithmetic series, meaning every term has to be separated by the same amount. And so far, you haven't had any arithmetic or geometric series. All of your sequences, rather. All of your sequences have been of these nature here. So all I need to do is figure out a sub 1 and a sub 2. What's a sub 1?
Just plugging in 1, so it'd be 1, negative 3, and negative 2, so that comes out to be 6, so it'd just be 6.
It's a sub 2.
Negative 2 times negative 1 times 2, it would be 2 times 2 equals 4, so 4.
Now, S sub 5 should be 5 over 2 times 6 plus 4, which is
Okay.
25. Now, let's just check them out. It's not
Okay.
hard to do. What's a sub 3? 0. In other words,
Okay.
instantly that becomes 0, right?
Oh yeah, so everything becomes 0.
Yeah, so I don't care what anything else is. Once I got a 0 as part of these three terms, I know what the product is.
Yeah.
A sub 4 is 0.
0.
But I'll bet you a sub 5 is 15.
Okay.
Because it's 5 times 1 times 2. I was wrong. How does that not come out to be 15? I mean, your formula may not be right.
That's interesting. Hold on one second. Let me look at my formula again.
Did I do anything wrong here? Let's go back. A sub 1 was negative 3 times negative 2.
A sub n, n over 2, a sub 1 plus a sub n minus, oh. I wonder if it,
25 is what I get based on your formula.
No, I think the formula might have been, let me just check something real quick. I might have copied it down wrong.
You might have, because let's see if it works on the sum of the first two terms. That's 10 times 1. Yeah, it does work on the first two terms.
Hmm.
But on the first
You
three
have that.
terms, in other words, S sub 3,
Oh, whoops. I have the formula here. I'm
okay,
sorry.
that's all right. No, it's not. I'm glad we checked it. That's always a good way. The thing about these series and sequences is that if you forget a formula, you can always check it by doing a small numbered test. In other words, I
Mm,
didn't actually have, well, it would have been incorrect to check it on just those two because it would have come out to be correct. But when I
yeah.
did the first three, it would have been wrong, your formula.
Uh-huh.
So it's a little tricky. Yeah, you can't just check a couple terms. What's the exact formula?
S of n equals n over 2, a sub 1 plus a sub n.
That's the formula for an arithmetic sequence.
Yeah, that's the one that I have. And then I have,
Exact
um,
formula for the partial sum of an arithmetic sequence.
and then I have a sub n is equal to a sub 1 plus n minus 1d.
Hold on a second. A sub n equals what? A sub 1
A,
plus n, yeah, d is the common difference between each term.
mm,
In other words, this is usually where they start you out at when they start teaching you about sequences and series. This is an arithmetic series.
yeah, and the difference is the difference between each
Yeah, I'm
term in
trying to figure
sequence.
out how we're going to figure out what that is based on this. I guess I could try plugging it in. So
That's what they have us do on one of our examples.
S sub 5 is 5 over 2 times a sub 1.
And they say to plug it in when you don't know the last number of the sequence. If you don't know the
What
last
do you
number
plug,
being added
what do
on.
you plug in? Oh, you plug in
You
that?
Yeah, you'd plug in that for a sub n.
Okay, so we know the first number is 6.
Mm-hmm.
So it's going to be 6 plus n times n minus 4 times n minus 3.
Mm-hmm.
Now you just plug in 5 for n, I guess. Huh. Yeah. So
Yeah.
we'll see if this thing comes out to be, what did I got 20, I think, when I added it up. We'll see what we get. 6 plus 5 times 1 times 2. That's 16. Divided by 2 is 8. That's 40.
Oh, hold on. 6 times 5 plus 1 times 2. That becomes 5 times 2 equals 10 equals 16 times... Huh.
Now,
Yeah, it does become 40.
yeah, and yet I don't think this, in other words, if I add up, if I list the first 5 terms of the sequence, we got 6, 4, the third term was 0, the fourth term was 0, and the fifth term is 16. I add up those first 5 terms, I get 26. So I don't think that is the formula for an arithmetic sequence. And I'm not sure this is. This does not, no, this is not an arithmetic sequence. This goes 6, 4, 0, 0, 16. That's not an arithmetic sequence. An arithmetic
No.
sequence is every term is separated by a constant amount. Okay, so I don't think you can use that formula on this sequence.
Okay.
I'm not quite sure what formula works for the, I'd have to look in my book probably and figure it up. But yeah, I don't think that's it. That doesn't seem to work here.
Yeah, no.
Yeah, because the fifth term, how did I get a fifth term of 16 here? Oh, that's not correct. The fifth term is 10.
Yeah.
So the sequence acts
20.
for 20, and somehow we're getting 40.
Hmm.
I'm not sure what the answer is. I'd have to investigate that a little bit.
Yeah, that's okay. I'm kind of looking at it too, and I can't. I'll ask him about that tomorrow.
Okay.
That's not too hard.
Okay.
That's okay.
Nick, I'm glad it wasn't too tough. There's some tough subjects after, I mean, you can get into parametric equations, even conic sections. If you have to deal with rotated conic sections, that's brutally tough. So
Okay.
anything that you think might be extra tough, just give me a heads up.
Okay,
A
I will.
couple hours before the session. And that way, if I need to research it a little bit, I'll have a little time to do so.
Okay.
All right?
Cool.
All right, Nick.
Thank you, Mr. Cohn.
Have a good one.
You too.
Bye-bye.
Bye-bye. And happy Mother's Day, by the way.
Well, thank you.
Yeah.
Same to your mom, Nikki. Tell her happy Mother's Day.
Mm-hmm.
All right.
Will do.
Bye-bye.
Bye-bye.